Memory management. The main purpose of a computer system is to execute programs. These programs, together with the data they access, must be at least partially in main memory during execution. To improve both the utilization of the CPU and the speed of its response to users, a general-purpose computer must keep several processes in memory. Many memory management schemes exist, reflecting various approaches, and the effectiveness of each algorithm depends on the situation. Selection of a memory management scheme for a system depends on many factors, especially on the hardware design of the system. Most algorithms require hardware support. Memory is central to the operation of a modern computer system. Memory consists of a large array of bytes, each with its own address. The CPU fetches instructions from memory according to the value of the program counter. These instructions may cause additional loading from and storing to specific memory addresses. A typical instruction execution cycle, for example, first fetches an instruction from memory. The instruction is then decoded and may cause operands to be fetched from memory. After the instruction has been executed on the operands, results may be stored back in memory. The memory unit sees only a stream of memory addresses. It does not know how they are generated by the instruction counter, indexing, indirection, literal addresses, and so on, or what they are for, instructions or data. Accordingly, we can ignore how a program generates a memory address. We are interested only in the sequence of memory addresses generated by the running program. We begin our discussion by covering several issues that are pertinent to managing memory: basic hardware, the binding of symbolic memory addresses to actual physical addresses, and the distinction between logical and physical addresses. We conclude the section with a discussion of dynamic linking and shared libraries. Basic hardware. Main memory and the registers built into the processor itself are the only general-purpose storage that the CPU can access directly. There are machine instructions that take memory addresses as arguments, but none that take disk addresses. Therefore, any instructions in execution and any data being used by the instructions must be in one of these direct access storage devices. If the data are not in memory, they must be moved there before the CPU can operate on them. Registers that are built into the CPU are generally accessible within one cycle of the CPU clock. Most CPUs can decode instructions and perform simple operations on register contents at the rate of one or more operations per clock tick. The same cannot be said of main memory, which is accessed via a transaction on the memory bus. Completing a memory access may take many cycles of the CPU clock. In such cases, the processor normally needs to stall since it does not have the data required to complete the instruction that it is executing. The situation is intolerable because of the frequency of memory accesses. The remedy is to add fast memory between the CPU and main memory, typically on the CPU chip for fast access. To manage a cache built into the CPU, the hardware automatically speeds up memory access without any operating system control. Not only are we concerned with the relative speed of accessing physical memory, but we also must ensure correct operation. For proper system operation, we must protect the operating system from access by user processes. On multi-user systems, we must additionally protect user processes from one another. This protection must be provided by the hardware because the operating system doesn't usually intervene between the CPU and its memory accesses because of the resulting performance penalty. Hardware implements this protection in several different ways. Here we outline one possible implementation. We first need to make sure that each process has a separate memory space. Separate per-process memory space protects the processes from each other and is fundamental to having multiple processes loaded in memory for concurrent execution. To separate memory spaces, we need the ability to determine the range of legal addresses that the process may access and to ensure that the process can access only these legal addresses. We can provide this protection by using two registers, usually a base and a limit, as illustrated in figure below. The base register holds the smallest legal physical memory address. The limit register specifies the size of the range. For example, if the base register holds 300040 and the limit register is 120900, then the program can legally access all addresses from 300040 through 420939 inclusive. Protection of memory space is accomplished by having the CPU hardware compare every address generated in user mode with the registers. Any attempt by a program executing in user mode to access operating system memory or other users' memory results in a trap to the operating system, which treats the attempt as a fatal error, figure below. This scheme prevents a user program from accidentally or deliberately modifying the code or data structures of either the operating system or other users. The base and limit registers can be loaded only by the operating system, which uses a special privileged instruction. Since privileged instructions can be executed only in kernel mode, and since only the operating system executes in kernel mode, only the operating system can load the base and limit registers. This scheme allows the operating system to change the value of the registers but prevents user programs from changing the register's contents. The operating system executing in kernel mode is given unrestricted access to both operating system memory and user's memory. This provision allows the operating system to load users' programs into users' memory, to dump out those programs in case of errors, to access and modify parameters of system calls, to perform input-output to and from user memory, and to provide many other services. Consider, for example, that an operating system for a multiprocessing system must execute context switches, storing the state of one process from the registers into main memory before loading the next process's context from main memory into the registers. Address binding. Usually, a program resides on a disk as a binary executable file. To be executed, the program must be brought into memory and placed within a process. Depending on the memory management in use, the process may be moved between disk and memory during its execution. The processes on the disk that are waiting to be brought into memory for execution form the input queue. The normal single-tasking procedure is to select one of the processes in the input queue and to load that process into memory. As the process is executed, it accesses instructions and data from memory. Eventually, the process terminates and its memory space is declared available. Most systems allow a user process to reside in any part of the physical memory. Thus, although the address space of the computer may start at 00000, the first address of the user process need not be 00000. You will see later how a user program actually places a process in physical memory. In most cases, a user program goes through several steps, some of which may be optional, before being executed. Figure below. Addresses may be represented in different ways during these steps. Addresses in the source program are generally symbolic, such as the variable count. A compiler typically binds these symbolic addresses to relocatable addresses, such as 14 bytes from the beginning of this module. The linkage editor or loader in turn binds the relocatable addresses to absolute addresses, such as 74014. Each binding is a mapping from one address space to another. Classically, the binding of instructions and data to memory addresses can be done at any step along the way. Compile time. If you know at compile time where the process will reside in memory, then absolute code can be generated. For example, if you know that a user process will reside starting at location R, then the generated compiler code will start at that location and extend up from there. If at some later time the starting location changes, then it will be necessary to recompile this code. The MS-DOS.COM format programs are bound at compile time. Load time. If it is not known at compile time where the process will reside in memory, then the compiler must generate relocatable code. In this case, final binding is delayed until load time. If the starting address changes, we need only reload the user code to incorporate this changed value. Execution time. If the process can be moved during its execution from one memory segment to another, then binding must be delayed until runtime. Special hardware must be available for this scheme to work. Most general-purpose operating systems use this method. A major portion of this chapter is devoted to showing how these various bindings can be implemented effectively in a computer system and to discussing appropriate hardware support. Page replacement algorithms. In our earlier discussion of the page fault rate, we assumed that each page faults at most once when it is first referenced. This representation is not strictly accurate, however. If a process of 10 pages actually uses only half of them, then demand paging saves the input-output necessary to load the 5 pages that are never used. We could also increase our degree of multiprogramming by running twice as many processes. Thus, if we had 40 frames, we could run 8 processes rather than the 4 that could run if each required 10 frames, 5 of which are never used. If we increase our degree of multiprogramming, we are over-allocating memory. If we run 6 processes, each of which is 10 pages in size but actually uses only 5 pages, we have higher CPU utilization and throughput with 10 frames to spare. It is possible, however, that each of these processes for a particular data set may suddenly try to use all 10 of its pages, resulting in a need for 60 frames when only 40 are available. Further, consider that system memory is not used only for holding program pages. Buffers for input-output also consume a considerable amount of memory. This use can increase the strain on memory placement algorithms. Deciding how much memory to allocate to input-output and how much to program pages is a significant challenge. Some systems allocate a fixed percentage of memory for input-output buffers, whereas others allow both user processes and the input-output subsystem to compete for all system memory. Over-allocation of memory manifests itself as follows. While a user process is executing, a page fault occurs. The operating system determines where the desired page is residing on the disk, but then finds that there are no free frames on the free frame list. All memory is in use. The operating system has several options at this point. It could terminate the user process. However, demand paging is the operating system's attempt to improve the computer system's utilization and throughput. Users should not be aware that their processes are running on a page system. Paging should be logically transparent to the user, so this option is not the best choice. The operating system could instead swap out a process, freeing all its frames and reducing the level of multiprogramming. This option is a good one in certain circumstances. Here, we discuss the most common solution, page replacement. Basic page replacement. Page replacement takes the following approach. If no frame is free, we find one that is not currently being used and free it. We can free a frame by writing its contents to swap space and changing the page table and all other tables to indicate that the page is no longer in memory. We can now use the freed frame to hold the page for which the process faulted. We modified the page fault service routine to include page replacement. Find the location of the desired page on the disk. Find a free frame. If there's a free frame, use it. If there is no free frame, use a page replacement algorithm to select a victim frame. Write the victim frame to the disk. Change the page and frame tables accordingly. Read the desired page into the newly freed frame. Change the page and frame tables. Continue the user process from where the page fault occurred. Notice that if no frames are free, 2 page transfers, one out and one in, are required. This situation effectively doubles the page fault service time and increases the effective access time accordingly. We can reduce this overhead by using a modify bit or dirty bit. When this scheme is used, each page or frame has a modify bit associated with it in the hardware. The modify bit for a page is set by the hardware whenever any byte in the page is written into, indicating that the page has been modified. When we select a page for replacement, we examine its modify bit. If the bit is set, we know that the page has been modified since it was read in from the disk. In this case, we must write the page to the disk. If the modify bit is not set, however, the page has not been modified since it was read into memory. In this case, we need not write the memory page to the disk. It is already there. This technique also applies to read-only pages, for example, pages of binary code. Such pages cannot be modified, thus they may be discarded when desired. This scheme can significantly reduce the time required to service a page fault since it reduces input-output time by 1/2 if the page has not been modified. Page replacement is basic to demand paging. It completes the separation between logical memory and physical memory. Within this mechanism, an enormous virtual memory can be provided for programmers on a smaller physical memory. With no demand paging, user addresses are mapped into physical addresses and the two sets of addresses can be different. All the pages of a process still must be in physical memory, however. With demand paging, the size of the logical address space is no longer constrained by physical memory. If we have a user process of 20 pages, we can execute it in 10 frames simply by using demand paging and using a replacement algorithm to find a free frame whenever necessary. If a page that has been modified is to be replaced, its contents are copied to the disk. A later reference to that page will cause a page fault. At that time, the page will be brought back into memory, perhaps replacing some other page in the process. We must solve two major problems to implement demand paging. We must develop a frame allocation algorithm and a page replacement algorithm. That is, if we have multiple processes in memory, we must decide how many frames to allocate to each process, and when page replacement is required, we must select the frames that are to be replaced. Designing appropriate algorithms to solve these problems is an important task because disk input-output is so expensive. Even slight improvements in demand paging methods yield large gains in system performance. There are many different page replacement algorithms. Every operating system probably has its own replacement scheme. How do we select a particular replacement algorithm? In general, we want the one with the lowest page fault rate. We evaluate an algorithm by running it on a particular string of memory references and computing the number of page faults. The string of memory references is called a reference string. We can generate reference strings artificially by using a random number generator, for example, or we can trace a given system and record the address of each memory reference. The latter choice produces a large number of data on the order of 1 million addresses per second. To reduce the number of data, we use two facts. First, for a given page size, and the page size is generally fixed by the hardware or system, we need to consider only the page number rather than the entire address. Second, if we have a reference to a page P, then any references to page P that immediately follow will never cause a page fault. Page P will be in memory after the first reference, so the immediately following references will not fault. For example, if we trace a particular process, we might record the following address sequence as follows. At 100 bytes per page, this sequence is reduced to the following reference string: 141 61 61 61 61. To determine the number of page faults for a particular reference string and page replacement algorithm, we also need to know the number of page frames available. Obviously, as the number of frames available increases, the number of page faults decreases. For the reference string considered previously, for example, if we had 3 or more frames, we would have only 3 faults, 1 fault for the first reference to each page. In contrast, with only 1 frame available, we would have a replacement with every reference, resulting in 11 faults. In general, we expect a curve such as that in figure below, graph of page faults versus page frames. As the number of frames increases, the number of page faults drops to some minimal level. Of course, adding physical memory increases the number of frames. We next illustrate several page replacement algorithms. In doing so, we use the reference string 7 0 1 2 0 3 0 4 2 3 0 3 2 1 2 0 1 7 0 1 for a memory with 3 frames. FIFO page replacement. The simplest page replacement algorithm is a first-in, first-out FIFO algorithm. A FIFO replacement algorithm associates with each page the time when the page was brought into memory. When a page must be replaced, the oldest page is chosen. Notice that it is not strictly necessary to record the time when a page is brought in. We can create a FIFO queue to hold all pages in memory. We replace the page at the head of the queue. When a page is brought into memory, we insert it at the tail of the queue. For our example reference string, our 3 frames are initially empty. The first 3 references, 7, 0, 1, cause page faults and are brought into these empty frames. The next reference 2 replaces page 7 because the page 7 was brought in first. Since 0 is the next reference and 0 is already in memory, we have no fault for this reference. The first reference to 3 results in replacement of page 0 since it is now first in line. Because of this replacement, the next reference to 0 will fault. Page 1 is then replaced by page 0. This process continues as shown in figure below, FIFO page replacement. Every time a fault occurs, we show which pages are in our 3 frames. There are 15 faults altogether. The FIFO page replacement algorithm is easy to understand and program. However, its performance is not always good. On the one hand, the page replaced may be an initialization module that was used a long time ago and is no longer needed. On the other hand, it could contain a heavily used variable that was initialized early and is in constant use. Notice that even if we select for replacement a page that is in active use, everything still works correctly. After we replace an active page with a new one, a fault occurs almost immediately to retrieve the active page. Some other page must be replaced to bring the active page back into memory. Thus, a bad replacement choice increases the page fault rate and slows process execution. It does not, however, cause incorrect execution. To illustrate the problems that are possible with a FIFO page replacement algorithm, consider the following reference string: 1, 2, 3, 4, 1, 2, 5, 1, 2, 3, 4, 5. Figure below shows the curve of page faults for this reference string versus the number of available frames. Notice that the number of faults for 4 frames, 10, is greater than the number of faults for 3 frames, 9. The most unexpected result is known as Beladi's anomaly. For some page replacement algorithms, the page fault rate may increase as the number of allocated frames increases. We would expect that giving more memory to a process would improve its performance. In some early research, investigators noticed that this assumption was not always true. Beladi's anomaly was discovered as a result. Optimal page replacement. One result of the discovery of Beladi's anomaly was the search for an optimal page replacement algorithm, the algorithm that has the lowest page fault rate of all algorithms and will never suffer from Beladi's anomaly. Such an algorithm does exist and has been called OPT or MIN. It is simply this: replace the page that will not be used for the longest period of time. Use of this page replacement algorithm guarantees the lowest possible page fault rate for a fixed number of frames. For example, on our sample reference string, the optimal page replacement algorithm would yield 9 page faults as shown in figure below. The first 3 references cause faults that fill the 3 empty frames. The reference to page 2 replaces page 7 because page 7 will not be used until reference 18, whereas page 0 will be used at 5 and page 1 at 14. The reference to page 3 replaces page 1 as page 1 will be the last of the 3 pages in memory to be referenced again. With only 9 page faults, optimal replacement is much better than a FIFO algorithm, which results in 15 faults. If we ignore the first 3, which all algorithms must suffer, then optimal replacement is twice as good as FIFO replacement. In fact, no replacement algorithm can process this reference string in 3 frames with fewer than 9 faults. Unfortunately, the optimal page replacement algorithm is difficult to implement because it requires future knowledge of the reference string. We encountered a similar situation with the SJF CPU scheduling algorithm. As a result, the optimal algorithm is used mainly for comparison studies. For instance, it may be useful to know that although a new algorithm is not optimal, it is within 12.3% of optimal at worst and within 4.7% on average. LRU page replacement. If the optimal algorithm is not feasible, perhaps an approximation of the optimal algorithm is possible. The key distinction between the FIFO and OPT algorithms, other than looking backward versus forward in time, is that the FIFO algorithm uses the time when a page was brought into memory, whereas the OPT algorithm uses the time when a page is to be used. If we use the recent past as an approximation of the near future, then we can replace the page that has not been used for the longest period of time. This approach is the least recently used LRU algorithm. LRU replacement associates with each page the time of that page's last use. When a page must be replaced, LRU chooses the page that has not been used for the longest period of time. We can think of this strategy as the optimal page replacement algorithm looking backward in time rather than forward. Strangely, if we let SR be the reverse of a reference string S, then the page fault rate for the OPT algorithm on S is the same as the page fault rate for the OPT algorithm on SR. Similarly, the page fault rate for the LRU algorithm on S is the same as the page fault rate for the LRU algorithm on SR. The result of applying LRU replacement to our example reference string is shown in figure below. The LRU algorithm produces 12 faults. Notice that the first 5 faults are the same as those for optimal replacement. When the reference to page 4 occurs, however, LRU replacement sees that of the 3 frames in memory, page 2 was used least recently. Thus, the LRU algorithm replaces page 2, not knowing that page 2 is about to be used. When it then falls for page 2, the LRU algorithm replaces page 3, since it is now the least recently used of the 3 pages in memory. Despite these problems, LRU replacement with 12 falls is much better than FIFO replacement with 15. The LRU policy is often used as a page replacement algorithm and is considered to be good. The major problem is how to implement LRU replacement. An LRU page replacement algorithm may require substantial hardware assistance. The problem is to determine an order for the frames defined by the time of last use. 2 implementations are feasible. Counters. In the simplest case, we associate with each page table entry a time of use field and add to the CPU a logical clock or counter. The clock is incremented for every memory reference. Whenever a reference to a page is made, the contents of the clock register are copied to the time of use field in the page table entry for that page. In this way, we also have the time of the last reference to each page. We replace the page with the smallest time value. This scheme requires a search of the page table to find the LRU page and write to memory to the time of use field in the page table for each memory access. The times must also be maintained when page tables are changed due to CPU scheduling. Overflow of the clock must be considered. Stack. Another approach to implementing LRU replacement is to keep a stack of page numbers. Whenever a page is referenced, it is removed from the stack and put on the top. In this way, the most recently used page is always at the top of the stack and the least recently used page is always at the bottom. Figure below. Because entries must be removed from the middle of the stack, it is best to implement this approach by using a doubly linked list with a head pointer and a tail pointer. Removing a page and putting it on the top of the stack then requires changing 6 pointers at worst. Each update is a little more expensive, but there is no search for a replacement. The tail pointer points to the bottom of the stack, which is the LRU page. This approach is particularly appropriate for software or microcode implementations of LRU replacement. Like optimal replacement, LRU replacement does not suffer from Belode's anomaly. Both belong to a class of page replacement algorithms called stack algorithms that can never exhibit Belode's anomaly. A stack algorithm is an algorithm for which it can be shown that the set of pages in memory for n frames is always a subset of the set of pages that would be in memory with n plus 1 frames. For LRU replacement, the set of pages in memory would be the n most recently referenced pages. If the number of frames is increased, then n pages will still be the most recently referenced and so will still be in memory. Note that neither implementation of LRU would be conceivable without hardware assistance beyond the standard TLB registers. The updating of the clock fields or stack must be done for every memory reference. If we were to use an interrupt for every reference to allow software to update such data structures, it would slow every memory reference by a factor of at least 10, hence slowing every user process by a factor of 10. Few systems could tolerate that level of overhead for memory management. LRU approximation page replacement. Few computer systems provide sufficient hardware support for the true LRU page replacement. In fact, some systems provide no hardware support, and other page replacement algorithms, such as a FIFO algorithm, must be used. Many systems provide some help, however, in the form of a reference bit. The reference bit for a page is set by the hardware whenever that page is referenced, either a read or a write to any byte in the page. Reference bits are associated with every entry in the page table. Initially, all bits are cleared to 0 by the operating system. As a user process executes, the bit associated with each page referenced is set to 1 by the hardware. After some time, we can determine which pages have been used and which have not been used by examining the reference bits, although we do not know the order of use. This information is the basis for many page replacement algorithms that approximate LRU replacement. Additional reference bits algorithm. We can gain additional ordering information by recording the reference bits at regular intervals. We can keep an 8-bit byte for each page in a table in memory. At regular intervals, say every 100 milliseconds, a timer interrupt transfers control to the operating system. The operating system shifts the reference bit for each page into the high order bit of its 8-bit byte, shifting the other bits right by 1 bit and discarding the lower order bit. These 8-bit shift registers contain the history of page use for the last 8 time periods. If the shift register contains 00000000, for example, then the page has not been used for 8 time periods. A page that is used at least once in each period has a shift register value of 11111111. A page with a history register value of 11000100 has been used more recently than one with a value of 01110111. If we interpret these 8-bit bytes as unsigned integers, the page with the lowest number is the LRU page and it can be replaced. Notice that the numbers are not guaranteed to be unique, however. We can either swap out all pages with the smallest value or use the FIFO method to choose among them. The number of bits of history included in the shift register can be varied, of course, and is selected depending on the hardware available to make the updating as fast as possible. In the extreme case, the number can be reduced to 0, leaving only the reference bit itself. This algorithm is called the second chance page replacement algorithm. Second chance algorithm. The basic algorithm of second chance replacement is a FIFO replacement algorithm. When a page has been selected, however, we inspect its reference bit. If the value is 0, we proceed to replace this page, but if the reference bit is set to 1, we give the page a second chance and move on to select the next FIFO page. When a page gets a second chance, its reference bit is cleared and its arrival time is reset to the current time. Thus, a page that is given a second chance will not be replaced until all other pages have been replaced or given second chances. In addition, if a page is used often enough to keep its reference bit set, it will never be replaced. One way to implement the second chance algorithm, sometimes referred to as the clock algorithm, is as a circular queue. A pointer, that is, a hand on the clock, indicates which page is to be replaced next. When a frame is needed, the pointer advances until it finds a page with a 0 reference bit. As it advances, it clears the reference bits. Figure shows second chance clock page replacement algorithm. Once a victim page is found, the page is replaced and the new page is inserted in the circular queue in that position. Notice that in the worst case, when all bits are set, the pointer cycles through the whole queue, giving each page a second chance. It clears all the reference bits before selecting the next page for replacement. Second chance replacement degenerates to FIFO replacement if all bits are set. Enhanced second chance algorithm. We can enhance the second chance algorithm by considering the reference bit and the modify bit as an ordered pair. With these two bits, we have the following 4 possible classes. 00, neither recently used nor modified, best page to replace. 01, not recently used but modified, not quite as good because the page will need to be written out before replacement. 10, recently used but clean, probably will be used again soon. 11, recently used and modified, probably will be used again soon, and the page will need to be written out to disk before it can be replaced. Each page is in one of these 4 classes. When page replacement is called for, We use the same scheme as in the clock algorithm, but instead of examining whether the page to which we are pointing has the reference bit set to 1, we examine the class to which that page belongs. We replace the first page encountered in the lowest non-empty class. Notice that we may have to scan the circular queue several times before we find a page to be replaced. The major difference between this algorithm and the simpler clock algorithm is that here we give preference to those pages that have been modified in order to reduce the number of input outputs required. Counting-based page replacement. There are many other algorithms that can be used for page replacement. For example, we can keep a counter of the number of references that have been made to each page and develop the following two schemes. The least frequently used LFU. The LFU page replacement algorithm requires that the page with the smallest count be replaced. The reason for the selection is that an actively used page should have a large reference count. A problem arises, however, when a page is used heavily during the initial phase of a process but then is never used again. Since it was used heavily, it has a large count and remains in memory even though it is no longer needed. One solution is to shift the counts right by 1 bit at regular intervals, forming an exponentially decaying average usage count. The most frequently used, MFU. The MFU page replacement algorithm is based on the argument that the page with the smallest count was probably just brought in and has yet to be used. As you might expect, neither MFU nor LFU replacement is common. The implementation of these algorithms is expensive and they do not approximate OPT replacement well. Page buffering algorithms. Other procedures are often used in addition to a specific page replacement algorithm. For example, systems commonly keep a pool of free frames. When a page fault occurs, a victim frame is chosen as before. However, the desired page is read into a free frame from the pool before the victim is written out. This procedure allows the process to restart as soon as possible without waiting for the victim page to be written out. When the victim is later written out, its frames is added to the free frame pool. An expansion of this idea is to maintain a list of modified pages. Whenever the paging device is idle, a modified page is selected and is written to the disk. Its modified bit is then reset. This scheme increases the probability that a page will be clean when it is selected for replacement and will not need to be written out. Another modification to keep a pool of free frames but to remember which page was in each frame. Since the frame contents are not modified when a frame is written to the disk, the old page can be reused directly from the free frame pool if it is needed before that frame is reused. No input-output is needed in this case. When a page fault occurs, we first check whether the desired page is in the free frame pool. If it is not, we must select a free frame and read into it. This technique is used in the VAX BMS system along with a FIFO replacement algorithm. When the FIFO replacement algorithm mistakenly replaces a page that is still in active use, that page is quickly retrieved from the free frame pool and no input-output is necessary. The free frame buffer provides protection against the relatively poor but simple FIFO replacement algorithm. This method is necessary because the early versions of VAX did not implement the reference bit correctly. Some versions of the Unix system use this method in conjunction with the second chance algorithm. It can be a useful augmentation to any page replacement algorithm to reduce the penalty incurred if the wrong victim page is selected. Applications and page replacement. In certain cases, applications accessing data through the operating system's virtual memory perform worse than if the operating system provided no buffering at all. A typical example is a database which provides its own memory management and input-output buffering. Applications like this understand their memory use and disk use better than does an operating system that is implementing algorithms for general-purpose use. If the operating system is buffering input-output and the application is doing so as well, however, then twice the memory is being used for a set of input-output. In another example, data warehouses frequently perform massive sequential disk reads followed by computations and writes. The LRU algorithm would be removing old pages and preserving new ones, while the application would more likely be reading older pages than newer ones as it starts its sequential reads again. Here, MFU would actually be more efficient than LRU. Because of such problems, some operating systems give special programs the ability to use a disk partition as a large sequential array of logical blocks without any file system data structures. This array is sometimes called the raw disk, and input-output to this array is termed raw input-output. Raw input-output bypasses all the file system services such as file input-output demand paging, file locking, prefetching, space allocation, file names, and directories. Notice that although certain applications are more efficient when implementing their own special-purpose storage services on a raw partition, most applications perform better when they use the regular file system services. Paging. Segmentation permits the physical address space of a process to be non-contiguous. Paging is another memory management scheme that offers this advantage. However, paging avoids external fragmentation and the need for compaction, whereas segmentation does not. It also solves the considerable problem of fitting memory chunks of varying sizes onto the backing store. Most memory management schemes used before the introduction of paging suffered from this problem. The problem arises because when code fragments or data residing in main memory need to be swapped out, space must be found on the backing store. The backing store has the same fragmentation problems discussed in connection with main memory, but access is much slower, so compaction is impossible. Because of its advantages over earlier methods, paging in its various forms is used in most operating systems, from those for mainframes through those for smartphones. Paging is implemented through cooperation between the operating system and the computer hardware. Basic method. The basic method for implementing paging involves breaking physical memory into fixed size blocks called frames and breaking logical memory into blocks of the same size called pages. When a process is to be executed, its pages are loaded into any available memory frames from their source, a file system, or the backing store. The backing store is divided into fixed-sized blocks that are the same size as the memory frames or clusters of multiple frames. This rather simple idea has great functionality and wide ramifications. For example, the logical address space is now totally separate from the physical address space, so a process can have a logical 64-bit address space even though the system has less than 264 bytes of physical memory. The hardware support for paging is illustrated in figure below. Every address generated by the CPU is divided into two parts, a page number P and a page offset D. The page number is used as an index into a page table. The page table contains the base address of each page in physical memory. This base address is combined with the page offset to define the physical memory address that is sent to the memory unit. The paging model of logical and physical memory is shown in figure below. The page size, like the frame size, is defined by the hardware. The size of a page is a power of 2, varying between 512 bytes and 1 GB per page, depending on the computer architecture. The selection of a power of 2 as a page size makes the translation of a logical address into a page number and page offset particularly easy. If the size of the logical address space is 2M and a page size is 2N bytes, then the higher order m-n bits of a logical address designate the page number and the n low order bits designate the page offset. Thus, the logical address is as follows, where P is an index into the page table and D is the displacement within the page. As a concrete, although minuscule example, consider the memory in figure below. Paging example for a 32-byte memory with 4-byte pages. Here in the logical address, n equals 2 and m equals 4. Using a page size of 4 bytes and a physical memory of 32 bytes, 8 pages, we show how the programmer's view of memory can be mapped into physical memory. Logical address 0 is page 0, offset 0. Indexing into the page table, we find that page 0 is in frame 5. Thus, logical address 0 maps to physical address 20 equals 5 times 4 plus 0. Logical address 3, page 0, offset 3, maps to physical address 23 equals 5 times 4 plus 3. Logical address 4 is page 1, offset 0. According to the page table, page 1 is mapped to frame 6. Thus, logical address 4 maps to physical address 24 equals 6 times 4 plus 0. Logical address 13 maps to physical address 9. You may have noticed that paging itself is a form of dynamic relocation. Every logical address is bound by the paging hardware to some physical address. Using paging is similar to using a table of base or relocation registers, one for each frame of memory. When we use a paging scheme, we have no external fragmentation. Any free frame can be allocated to a process that needs it. However, we may have some internal fragmentation. Notice that frames are allocated as units. If the memory requirements of a process do not happen to coincide with page boundaries, the last frame allocated may not be completely full. For example, if page size is 2048 bytes, a process of 72,766 bytes will need 35 pages plus 1086 bytes. It will be allocated 36 frames, resulting in internal fragmentation of 2048 minus 1086 equaling 962 bytes. In the worst case, a process would need n pages plus 1 byte. It would be allocated n plus 1 frames, resulting in internal fragmentation of almost an entire frame. If process size is independent of page size, we expect internal fragmentation to average 1/2 page per process. This consideration suggests that small page sizes are desirable. However, overhead is involved in each page table entry, and this overhead is reduced as the size of the pages increases. Also, disk input-output is more efficient when the amount data being transferred is larger. Generally, page sizes have grown over time as processes, data sets, and main memory have become larger. Today, pages typically are between 4 kilobytes and 8 kilobytes in size, and some systems support even larger page sizes. Some CPUs and kernels even support multiple page sizes. For instance, Solaris uses page sizes of 8 kilobytes and 4 megabytes depending on the data stored by the pages. Researchers are now developing support for variable on-the-fly page size. Frequently, on a 32-bit CPU, each page table entry is 4 bytes long, but that size can vary as well. A 32-bit entry can point to one of the 232 physical page frames. If frame size is 4 kilobytes, 212, then a system with 4-byte entries can address 244 bytes or 16 terabytes of physical memory. We should note here that the size of physical memory in a paged memory system is different from the maximum logical size of a process. As we further explore paging, we introduce other information that must be kept in the page table entries. That information reduces the number of bits available to address page frames. Thus, a system with 32-bit page table entries may address less physical memory than the possible maximum. A 32-bit CPU uses 32-bit addresses, meaning that a given process space can only be 232 bytes or 4 terabyte. Therefore, paging lets us use physical memory that is larger than what can be addressed by the CPU's address pointer length. When a process arrives in the system to be executed, its size, expressed in pages, is examined. Each page of the process needs 1 frame. Thus, if the process requires n pages, at least n frames must be available in memory. If n frames are available, they are allocated to this arriving process. The first page of the process is loaded into one of the allocated frames, and the frame number is put in the page table for this process. The next page is loaded into another frame, its frame number is put into the page table, and so on. Figure below shows 3 frames. A. Before allocation. B. After allocation. An important aspect of paging is the clear separation between the programmer's view of memory and the actual physical memory. The programmer views memory as one single space containing only this one program. In fact, the user program is scattered throughout physical memory, which also holds other programs. The difference between the programmer's view of memory and the actual physical memory is reconciled by the address translation hardware. The logical addresses are translated into physical addresses. This mapping is hidden from the programmer and is controlled by the operating system. Notice that the user process by definition is unable to access memory it does not own. It has no way of addressing memory outside of its page table, and the table includes only those pages that the process owns. Since the operating system is managing physical memory, it must be aware of the allocation details of physical memory, which frames are allocated, which frames are available, how many total frames are there, and so on. This information is generally kept in a data structure called a frame table. The frame table has one entry for each physical page frame, indicating whether the latter is free or allocated, and, if it is allocated, to which page of which process or processes. In addition, the operating system must be aware that user processes operate in user space, and all logical addresses must be mapped to produce physical addresses. If a user makes a system call to do input-output, for example, and provides an address as a parameter, a buffer, for instance, that address must be mapped to produce the correct physical address. The operating system maintains a copy of the page table for each process, just as it maintains a copy of the instruction counter and register contents. This copy is used to translate logical addresses to physical addresses whenever the operating system must map a logical address to a physical address manually. It is also used by the CPU dispatcher to define the hardware page table when a process is to be allocated the CPU. Paging therefore increases the context switch time. Hardware support. Each operating system has its own methods for storing page tables. Some allocate a page table for each process. A pointer to the page table is stored with the other register values, like the instruction counter in the process control block. When the dispatcher is told to start a process, it must reload the user registers and define the correct hardware page table values from the stored user page table. Other operating systems provide one or at most a few page tables, which decreases the overhead involved when processes are context switched. The hardware implementation of page table can be done in several ways. In the simplest case, the page table is implemented as a set of dedicated registers. These registers should be built with very high-speed logic to make the paging address translation efficient. Every access to memory must go through the paging map, so efficiency is a major consideration. The CPU dispatcher reloads these registers just as it reloads the other registers. Instructions to load or modify the page table registers are, of course, privileged so that only the operating system can change the memory map. The DEC PDP-11 is an example of such an architecture. The address consists of 16 bits and the page size is 8 KB. The page table thus consists of 8 entries that are kept in fast registers. The use of registers for the page table is satisfactory if the page table is reasonably small, for example, 256 entries. Most contemporary computers, however, allow the page table to be very large, for example, 1 million entries. For these machines, the use of fast registers to implement the page table is not feasible. Rather, the page table is kept in main memory and a page table base register, PTBR, points to the page table. Changing page tables requires changing only this one register, substantially reducing context switch time. The problem with this approach is the time required to access a user memory location. If we want to access location I, we must first index into the page table using the value in the PTBR offset by the page number for I. This task requires a memory access. It provides us with the frame number, which is combined with the page offset to produce the actual address. We can then access the desired place in memory. With this scheme, 2 memory accesses are needed to access a byte, one for the page table entry, one for the byte. Thus, memory access is slowed by a factor of 2. This delay would be intolerable under most circumstances. We might as well resort to swapping. The standard solution to this problem is to use a special, small, fast lookup hardware cache called a Translation Look-Aside Buffer, TLB. The TLB is associative high-speed memory. Each entry in the TLB consists of 2 parts, a key or tag and a value. When the associative memory is presented with an item, the item is compared with all keys simultaneously. If the item is found, the corresponding value field is returned. The search is fast. A TLB lookup in modern hardware is part of the instruction pipeline, essentially adding no performance penalty. To be able to execute the search within a pipeline step, however, the TLB must be kept small. It is typically between 32 and 1024 entries in size. Some CPUs implement separate instruction and data address TLBs. That can double the number of TLB entries available because those lookups occur in different pipeline steps. We can see in this development an example of the evolution of CPU technology. Systems have evolved from having no TLBs to having multiple levels of TLBs, just as they have multiple levels of caches. The TLB is used with page tables in the following way. The TLB contains only a few of the page table entries. When a logical address is generated by the CPU, its page number is presented to the TLB. If the page number is found, its frame number is immediately available and is used to access memory. As just mentioned, these steps are executed as part of the instruction pipeline within the CPU, adding no performance penalty compared with a system that does not implement paging. If the page number is not in the TLB, known as a TLB miss, a memory reference to the page table must be made. Depending on the CPU, this may be done automatically in hardware or via an interrupt to the operating system. When the frame number is obtained, we can use it to access memory. Figure below shows paging hardware with TLB. In addition, we add the page number and frame number to the TLB so that they will be found quickly on the next reference. If the TLB is already full of entries, an existing entry must be selected for replacement. Replacement policies range from least recently used LRU through round-robin to random. Some CPUs allow the operating system to participate in LRU entry replacement, while others handle the matter themselves. Furthermore, some TLBs allow certain entries to be wired down, meaning that they cannot be removed from the TLB. Typically, TLB entries for key kernel code are wired down. Some TLBs store address space identifiers, ASIDs, in each TLB entry. An ASID uniquely identifies each process and is used to provide address space protection for that process. When the TLB attempts to resolve virtual page numbers, it ensures that the ASID for the currently running process matches the ASID associated with the virtual page. If the ASIDs do not match, the attempt is treated as a TLB miss. In addition to providing address space protection, an ASID allows a TLB to contain entries for several different processes simultaneously. If the TLB does not support separate ASIDs, then every time a new page table is selected, for instance with each context switch, the TLB must be flushed or erased to ensure that the next executing process does not use the wrong translation information. Otherwise, the TLB could include all entries that contain valid virtual addresses but have incorrect or invalid physical addresses left over from the previous process. The percentage of times that the page number of interest is found in the TLB is called the hit ratio. An 80% hit ratio, for example, means that we find the desired page number in the TLB 80% of the time. If it takes 100 nanoseconds to access memory, then a mapped memory access takes 100 nanoseconds when the page number is in the TLB. If we fail to find the page number in the TLB, then we must first access memory for the page table and frame number 100 nanoseconds and then access the desired byte in memory 100 nanoseconds for a total of 200 nanoseconds. We are assuming that a page table lookup takes only one memory access, but it can take more, as we shall see. To find the effective memory access time, we weight the case by its probability. Effective access time equals 0.80 times 100 plus 0.20 times 200 equals 120 nanoseconds. In this example, we suffer a 20% slowdown in average memory access time from 100 to 120 nanoseconds. For a 99% hit ratio, which is much more realistic, we have effective access time equals 0.99 times 100 plus 0.01 times 200 equals 101 nanoseconds. This increased hit rate produces only a 1% slowdown in access time. As we noted earlier, CPUs today may provide multiple levels of TLBs. Calculating memory access times in modern CPUs is therefore much more complicated than shown in the example above. For instance, the Intel Core i7 CPU has a 128-entry L1 instruction TLB and a 64-entry L1 data TLB. In the case of a miss at L1, it takes the CPU 6 cycles to check for the entry in the L2 512-entry TLB. A miss in L2 means that the CPU must either walk through the page table entries in memory to find the associated frame address, which can take hundreds of cycles, or interrupt to the operating system to have it to do the work. A complete performance analysis of paging overhead in such a system would require miss rate information about each TLB tier. We can see from the general information above, however, that hardware features can have a significant effect on memory performance and that operating system improvements, such as paging, can result in and, in turn, be affected by hardware changes such as TLBs. TLBs are a hardware feature and therefore would seem to be of little concern to operating systems and their designers. But the designer needs to understand the function and features of TLBs, which vary by hardware platform. For optimal operation, an operating system design for a given platform must implement paging according to the platform's TLB design. Likewise, a change in the TLB design, for example, between generations of Intel CPUs may necessitate a change in the paging implementation of the operating systems that use it. Memory protection in a paged environment is accomplished by protection bits associated with each frame. Normally, these bits are kept in the page table. One bit can define a page to be read-write or read-only. Every reference to memory goes through the page table to find the correct frame number. At the same time that the physical address is being computed, the protection bits can be checked to verify that no writes are being made to a read-only page. An attempt to write to a read-only page causes a hardware trap to the operating system or memory protection violation. We can easily expand this approach to provide a finer level of protection. We can create hardware to provide read-only, read-write or execute-only protection, or by providing separate protection bits for each kind of access, we can allow any combination of these accesses. Illegal attempts will be trapped to the operating system. One additional bit is generally attached to each entry in the page table, a valid-invalid bit. When this bit is set to valid, the associated page is in the processor's logical address space and is thus a legal or valid page. When the bit is set to invalid, the page is not in the processor's logical address space. Illegal addresses are trapped by use of the valid-invalid bit. The operating system sets this bit for each page to allow or disallow access to the page. Suppose, for example, that in a system with a 14-bit address space 0 to 16,383, we have a program that should use only addresses 0 to 10,468. Given a page size of 2 kilobytes, we have the situation shown in figure below shows valid V and invalid I in the page table. Addresses in pages 0, 1, 2, 3, 4 and 5 are mapped normally through the page table. Any attempt to generate an address in pages 6 or 7, however, will find that the valid-invalid bit is set to invalid and the computer will trap to the operating system invalid page reference. Notice that this scheme has created a problem. Because the program extends only to address 10,468, any reference beyond that address is illegal. However, references to page 5 are classified as valid, so accesses to addresses up to 12,287 are valid. Only the addresses from 12,288 to 16,383 are invalid. This problem is a result of the 2 KB page size and reflects the internal fragmentation of paging. Rarely does a process use all its address range. In fact, many processes use only a small fraction of the address space available to them. It would be wasteful in these cases to create a page table with entries for every page in the address range. Most of this table would be unused but would take up valuable memory space. Some systems provide hardware in the form of a page table length register, PTLR, to indicate the size of the page table. This value is checked against every logical address to verify that the address is in the valid range for the process. Failure of this test causes an error trap to the operating system. Shared pages. An advantage of paging is the possibility of sharing common code. This consideration is particularly important in a time-sharing environment. Consider a system that supports 40 users, each of whom executes a text editor. If the text editor consists of 150 kilobytes of code and 50 kilobytes of data space, we need 8,000 kilobytes to support the 40 users. If the code is reentrant code or pure code, however, it can be shared as shown in figure below. Sharing of code in paging environment. Here we see 3 processes sharing a 3-page editor, each page 50 kilobyte in size. The large page size is used to simplify the figure. Each process has its own data page. Reentrant code is non-self-modifying code. It never changes during execution. Thus, two or more processes can execute the same code at the same time. Each process has its own copy of registers and data storage to hold the data for the process's execution. The data for two different processes will, of course, be different. Only one copy of the editor need to be kept in physical memory. Each user's page table maps onto the same physical copy of the editor, but data pages are mapped onto different frames. Thus, to support 40 users, we need only one copy of the editor, 150 kilobytes, plus 40 copies of the 50 kilobyte of data space per user. The total space required is now 2,150 kilobytes instead of 8,000 kilobytes, a significant saving. Other heavily used programs can also be shared: compilers, Windows systems, runtime libraries, database systems, and so on. To be shareable, the code must be reentrant. The read-only nature of shared code should not be left to the correctness of the code. The operating system should enforce this property. The sharing of memory among processes on a system is similar to the sharing of the address space of a task by threads. Furthermore, we described shared memory as a method of inter-process communication. Some operating systems implement shared memory using shared pages. Organizing memory according to pages provides numerous benefits in addition to allowing several processes to share the same physical pages. Partition. The layout of a disk can have many variations depending on the operating system. A disk can be sliced into multiple partitions, or a volume can span multiple partitions on multiple disks. The former layout is discussed here, while the latter, which is more appropriately considered, a form of RAID. Each partition can be either raw, containing no file system, or cooked, containing a file system. Raw disk is used where no file system is appropriate. Unix swap space can use a raw partition, for example, since it uses its own format on disk and does not use a file system. Likewise, some databases use raw disk and format the data to suit their needs. Raw disk can also hold information needed by disk RAID systems, such as bitmaps indicating which blocks are mirrored and which have changed and need to be mirrored. Similarly, raw disk can contain a miniature database holding RAID configuration information, such as which disks are members of each RAID set. Raw disk use. Boot information can be stored in a separate partition. Again, it has its own format because at boot time the system does not have the file system code loaded and therefore cannot interpret the file system format. Rather, boot information is usually a sequential series of blocks loaded as an image into memory. Execution of the image starts at a predefined location such as the first byte. This boot loader in turn knows enough about the file system structure to be able to find and load the kernel and start it executing. It can contain more than the instructions for how to boot a specific operating system. For instance, many systems can be dual booted, allowing us to install multiple operating systems on a single system. How does the system know which one to boot? A boot loader that understands multiple file systems and multiple operating systems can occupy the boot space. Once loaded, it can boot one of the operating systems available on the disk. The disk can have multiple partitions, each containing a different type of file system and a different operating system. The root partition, which contains the operating system kernel and sometimes other system files, is mounted at boot time. Other volumes can be automatically mounted at boot or manually mounted later, depending on the operating system. As part of a successful mount operation, the operating system verifies that the device contains a valid file system. It does so by asking the device driver to read the device directory and verifying that the directory has the expected format. If the format is invalid, the partition must have its consistency checked and possibly corrected either with or without user intervention. Finally, the operating system notes in its in-memory mount table that a file system is mounted along with the type of the file system. The details of this function depend on the operating system. Microsoft Windows-based systems mount each volume in a separate namespace denoted by a letter and a colon. To record that, a file system is mounted at F:. For example, the operating system places a pointer to the file system in a field of the device structure corresponding to F:. When a process specifies the driver letter, the operating system finds the appropriate file system pointer and traverses the directory structures on that device to find the specified file or directory. Later versions of Windows can mount a file system at any point within the existing directory structure. On Unix, the file systems can be mounted at any directory. Mounting is implemented by setting a flag in the in-memory copy of the inode for that directory. The flag indicates that the directory is a mount point. A field then points to an entry in the mount table indicating which device is mounted there. The mount table entry contains a pointer to the superblock of the file system on that device. This scheme enables the operating system to traverse its directory structure, switching seamlessly among file systems of varying types. Performance of demand paging. Demand paging can significantly affect the performance of a computer system. To see why, let's compute the effective access time for a demand-paged memory. For most computer systems, the memory access time, denoted MA, ranges from 10 to 200 nanoseconds. As long as we have no page faults, the effective access time is equal to the memory access time. If, however, a page fault occurs, we must first read the relevant page from disk and then access the desired word. Let P be the probability of a page fault, where 0 is less than or equal to P, which is less than or equal to 1. We would expect P to be close to 0, that is, we would expect to have only a few page faults. The effective access time is then effective access time equaling 1 minus P times MA plus P times page fault time. To compute the effective access time, we must know how much time is needed to service a page fault. A page fault causes the following sequence to occur. 1. Trap to the operating system. 2. Save the user registers and process state. 3. Determine that the interrupt was a page fault. 4. Check that the page reference was legal and determine the location of the page on the disk. 5. Issue a read from the disk to a free frame. Wait in a queue for this device until the read request is serviced. Wait for the device seek and/or latency time. Begin the transfer of the page to a free frame. 6. While waiting, allocate the CPU to some other user, CPU scheduling optional. 7. Receive an interrupt from the disk input-output subsystem, input-output completed. 8. Save the registers and process state for the other user if step 6 is executed. 9. Determine that the interrupt was from the disk. 10. Correct the page table and other tables to show that the desired page is now in memory. 11. Wait for the CPU to be allocated to this process again. 12. Restore the user registers, process state and new page table and then resume the interrupted instruction. Not all of these steps are necessary in every case. For example, we are assuming that in step 6, the CPU is allocated to another process while the input-output occurs. This arrangement allows multiprogramming to maintain CPU utilization but requires additional time to resume the page fault service routine when the input-output transfer is complete. In any case, we are faced with three major components of the page fault service time. Service the page fault interrupt, read in the page, restart the process. The first and third tasks can be reduced with careful coding to several hundred instructions. These tasks may take from 1 to 100 microseconds each. The page switch time, however, will probably be close to 8 milliseconds. A typical hard disk has an average latency of 3 milliseconds, a seek of 5 milliseconds, and a transfer time of 0.05 milliseconds. Thus, the total paging time is about 8 milliseconds, including hardware and software time. Remember also that we are looking at only the device service time. If a queue of processes is waiting for the device, we have to add device queuing time as we wait for the paging device to be free to service our request, increasing even more the time of swap. With an average page fault service time of 8 milliseconds and a memory access time of 200 nanoseconds, the effective access time in nanoseconds is effective access time equals to 1 minus p times 200 plus p brackets 8 milliseconds equals 1 minus p times 200 plus p times 8 million equals 200 plus 7,999,800 times p. We see then that the effective access time is directly proportional to the page fault rate. If one access out of 1000 causes a page fault, the effective access time is 8.2 microseconds. The computer will be slowed down by a factor of 40 because of demand paging. If we want performance degradation to be less than 10%, we need to keep the probability of page faults at the following level: 220 greater than 200 plus 7,999,800 times p, 20 greater than 7,999,800 times p, p lesser than 0.000025. That is, to keep the slowdown due to paging at a reasonable level, we can allow fewer than one memory access out of 399,990 to page fault. In sum, it is important to keep the page fault rate low in a demand paging system. Otherwise, the effective access time increases, slowing process execution dramatically. An additional aspect of demand paging is the handling and overall use of swap space. Disk input-output to swap space is generally faster than that to the file system. It is a faster file system because swap space is allocated in much larger blocks and file lookups and indirect allocation methods are not used. The system can therefore gain better paging throughput by copying an entire file image into the swap space at process startup and then performing demand paging from the swap space. Another option is to demand pages from the file system initially, but to write the pages to swap space as they are replaced. This approach will ensure that only needed pages are read from the file system, but that all subsequent paging is done from swap space. Some systems attempt to limit the amount of swap space used through demand paging of binary files. Demand pages for such files are brought directly from the file system. However, when page replacement is called for, these frames can simply be overwritten because they are never modified, and the pages can be read in from the file system again if needed. Using this approach, the file system itself serves as the backing store. However, swap space must still be used for pages not associated with a file known as anonymous memory. These pages include the stack and heap for a process. This method appears to be a good compromise and is used in several systems including Solaris and BSD Unix. Mobile operating systems typically do not support swapping. Instead, these systems demand page from the file system and reclaim read-only pages, such as code, from applications if memory becomes constrained. Such data can be demand-paged from the file system if it is later needed. Under iOS, anonymous memory pages are never reclaimed from an application unless the application is terminated or explicitly releases the memory. Protection. When information is stored in a computer system, we want to keep it safe from physical damage, the issue of reliability, and improper access, the issue of protection. Reliability is generally provided by duplicate copies of files. Many computers have system programs that automatically or through computer operator intervention copy disk files to tape at regular intervals, once per day or week or month, to maintain a copy should a file system be accidentally destroyed. File systems can be damaged by hardware problems such as errors in reading or writing, power surges or failures, head crashes, dirt, temperature extremes, and vandalism. Files may be deleted accidentally. Bugs in the file system software can also cause file contents to be lost. Protection can be provided in many ways. For a single-user laptop system, we might provide protection by locking the computer in a desk drawer or file cabinet. In a larger multi-user system, however, other mechanisms are needed. Types of access. The need to protect files is a direct result of the ability to access files. Systems that do not permit access to the files of other users do not need protection. Thus, we could provide complete protection by prohibiting access. Alternatively, we could provide free access with no protection. Both approaches are too extreme for general use. What is needed is controlled access. Protection mechanisms provide controlled access by limiting the types of file access that can be made. Access is permitted or denied depending on several factors, one of which is the type of access requested. Several different types of operations may be controlled. Read. Read from the file. Write. Write or rewrite the file. Execute. Load the file into memory and execute it. Append. Write new information at the end of the file. Delete. Delete the file and free its space for possible reuse. List. List the name and attributes of the file. Other operations such as renaming, copying, and editing the file may also be controlled. For many systems, however, these higher-level functions may be implemented by a system program that makes lower-level system calls. Protection is provided at only the lower level. For instance, copying a file may be implemented simply by a sequence of read requests. In this case, a user with read access can also cause the file to be copied, printed, and so on. Many protection mechanisms have been proposed. Each has advantages and disadvantages and must be appropriate for its intended application. A small computer system that is used by only a few members of a research group, for example, may not need the same types of protection as a large corporate computer that is used for research, finance, and personal operations. We discuss some approaches to protection in the following sections and present a more complete treatment. Access control. The most common approach to the protection problem is to make access dependent on the identity of the user. Different users may need different types of access to a file or directory. The most general scheme to implement identity-dependent access is to associate with each file and directory an access control list (ACL) specifying usernames and the types of access allowed for each user. When a user requests access to a particular file, the operating system checks the access list associated with that file. If that user is listed for the requested access, the access is allowed. Otherwise, a protection violation occurs and the user job is denied access to the file. This approach has the advantage of enabling complex access methodologies. The main problem with access lists is their length. If we want to allow everyone to read a file, we must list all users with read access. This technique has two undesirable consequences. Constructing such a list may be a tedious and unrewarding task, especially if we do not know in advance the list of users in the system. The directory entry, previously of fixed size, now must be of variable size, resulting in more complicated space management. These problems can be resolved by use of condensed version of the access list. To condense the length of the access control list, many systems recognize three classifications of users in connection with each file. Owner. The user who created the file is the owner. Group. A set of users who are sharing the file and need similar access is a group or work group. Universe. All other users in the system constitute the universe. The most common recent approach is to combine access control lists with a more general and easier to implement owner, group, and universe access control scheme just described. For example, Solaris uses the 3 categories of access by default, but allows access control lists to be added to specific files and directories when more fine-grained access control is desired. To illustrate, consider a person, Sarah, who is writing a new book. She has hired 3 graduate students, Jim, Dawn, and Jill, to help with the project. The text of the book is kept in a file named book.tex. The protection associated with this file is as follows. Sarah should be able to invoke all operations on the file. Jim, Dawn, and Jill should be able only to read and write the file. They should not be allowed to delete the file. All other users should be able to read but not write the file. Sarah is interested in letting as many people as possible read the text so that she can obtain feedback. To achieve such protection, we must create a new group, say text, with members Jim, Dawn, and Jill. The name of the group, text, must then be associated with the file book.tex, and the access rights must be set in accordance with the policy we have outlined. Now consider a visitor to whom Sarah would like to grant temporary access. The visitor cannot be added to the text group because that would give him access to all chapters. Because a file can be in only one group, Sarah cannot add another group to chapter 1. With the addition of access control list functionality, though, the visitor can be added to the access control list. For this scheme to work properly, permissions and access lists must be controlled tightly. This control can be accomplished in several ways. For example, in the Unix system, groups can be created and modified only by the manager of the facility or by any superuser. Thus, control is achieved through human interaction. With the more limited protection classification, only 3 fields are needed to define protection. Often, each field is a collection of bits and each bit either allows or prevents the access associated with it. For example, the Unix system defines 3 fields of 3 bits each, RWX, where R controls read access, W controls write access, and X controls execution. A separate field is kept for the file owner, for the file's group, and for all other users. In this scheme, 9 bits per file are needed to record protection information. Thus, for our example, the protection fields for the file book.tex are as follows. For the owner, Sarah, all bits are set. For the group text, the R and the W bits are set. And for the universe, only the R bit is set. One difficulty in combining approaches comes in the user interface. Users must be able to tell when the optional ACL permissions are set on a file. In the Solaris example, A+ is appended to the regular permissions as in 19 RW R R plus 1 Jim Staff 130 May 25 22:13 file 1. A separate set of commands setFACL and getFACL is used to manage the ACLs. Windows users typically manage access control lists via the GUI. Figure Windows 7 Access Control List Management shows a file permission window on Windows 7 NTFS file system. In this example, user guest is specifically denied access to the file listpanel.java. Another difficulty is assigning precedence when permission and ACLs conflict. For example, if Joe is in a files group which has read permission but the file has an ACL granting Joe read and write permission, should a write by Joe be granted or denied? Solaris gives ACLs precedence as they are more fine-grained and are not assigned by default. This follows the general rule that specificity should have priority. Other protection approaches. Another approach to the protection problem is to associate a password with each file. Just as access to the computer system is often controlled by a password, access to each file can be controlled in the same way. If the passwords are chosen randomly and changed often, the scheme may be effective in limiting access to a file. The use of passwords has a few disadvantages, however. First, the number of passwords that a user needs to remember may become large, making the scheme impractical. Second, if only one password is used for all the files, then once it is discovered all files are accessible, protection is on an all or none basis. Some systems allow a user to associate a password with a subdirectory rather than with an individual file to address this problem. In a multi-level directory structure, we need to protect not only individual files but also collections of files in subdirectories. That is, we need to provide a mechanism for directory protection. The directory operations that must be protected are somewhat different from the file operations. We want to control the creation and deletion of files in a directory. In addition, we probably want to control whether a user can determine the existence of a file in a directory. Sometimes knowledge of the existence and name of a file is significant in itself. Thus, listing the contents of a directory must be a protected operation. Similarly, if a path name refers to a file in a directory, the user must be allowed access to both the directory and the file. In systems where files may have numerous path names such as acyclic and general graphs, a given user may have different access rights to a particular file depending on the path name used. Recovery. Files and directories are kept both in main memory and on disk, and care must be taken to ensure that a system failure does not result in loss of data or in data inconsistency. We deal with these issues in this section. We also consider how a system can recover from such a failure. A system crash can cause inconsistencies among on-disk file system data structures such as directory structures, free block pointers, and free FCB pointers. Many file systems apply changes to these structures in place. A typical operation such as creating a file can involve many structural changes within the file system on the disk. Directory structures are modified, FCBs are allocated, data blocks are allocated, and free counts for all of these blocks are decreased. These changes can be interrupted by a crash, and inconsistencies among the structures can result. For example, the free FCB count might indicate that an FCB has been allocated, but the directory structure might not point to the FCB. Compounding this problem is the caching that operating systems do to optimize input-output performance. Some changes may go directly to disk while others may be cached. If the cached changes do not reach disk before a crash occurs, more corruption is possible. In addition to crashes, bugs in file system implementation, disk controllers, and even user applications can corrupt a file system. File systems have varying methods to deal with corruption depending on the file system data structures and algorithms. We deal with these issues next. Consistency checking. Whatever the cause of corruption, a file system must first detect the problems and then correct them. For detection, a scan of all the metadata on each file system can confirm or deny the consistency of the system. Unfortunately, the scan can take minutes or hours and should occur every time the system boots. Alternatively, a file system can record its state within the file system metadata. At the start of any metadata change, a status bit is set to indicate that the metadata is in flux. If all updates to the metadata complete successfully, the file system can clear that bit. If, however, the status bit remains set, a consistency checker is run. The consistency checker, a systems program such as FSCK in Unix, compares the data in the directory structure with the data blocks on disk and tries to fix any inconsistencies it finds. The allocation and free space management algorithms dictate what types of problems the checker can find and how successful it will be in fixing them. For instance, if linked allocation is used and there is a link from any block to its next block, then the entire file can be reconstructed from the data blocks and the directory structure can be recreated. In contrast, the loss of a directory entry on an indexed allocation system can be disastrous because the data blocks have no knowledge of one another. For this reason, Unix caches directory entries for reads. But any write that results in space allocation or other metadata changes is done synchronously before the corresponding data blocks are written. Of course, problems can still occur if a synchronous write is interrupted by a crash. Log-structured file systems. Computer scientists often find that algorithms and technologies originally used in one area are equally useful in other areas. Such is the case with the database log-based recovery algorithms. These logging algorithms have been applied successfully to the problem of consistency checking. The resulting implementations are known as log-based transaction-oriented or journaling file systems. Note that with the consistency checking approach discussed in the preceding section, we essentially allow structures to break and repair them on recovery. However, there are several problems with this approach. One is that the inconsistency may be irreparable. The consistency check may not be able to recover the structures, resulting in loss of files and even entire directories. Consistency checking can require human intervention to resolve conflicts, and that is inconvenient if no human is available. The system can remain unavailable until the human tells it how to proceed. Consistency checking also takes system and clock time. To check terabytes of data, hours of clock time may be required. The solution to this problem is to apply log-based recovery techniques to file system metadata updates. Both NTFS and the Veritas file system use this method, and it is included in recent versions of UFS on Solaris. In fact, it is becoming common on many operating systems. Fundamentally, all metadata changes are written sequentially to a log. Each set of operations for performing a specific task is a transaction. Once the changes are written to this log, they are considered to be committed, and the system call can return to the user process, allowing it to continue execution. Meanwhile, these log entries are replayed across the actual file system structures. As the changes are made, a pointer is updated to indicate which actions have completed and which are still incomplete. When an entire committed transaction is completed, it is removed from the log file, which is actually a circular buffer. A circular buffer writes to the end of its space and then continues at the beginning, overwriting older values as it goes. We would not want the buffer to write over data that had not yet been saved, so that scenario is avoided. The log may be in a separate section of the file system or even on a separate disk spindle. It is more efficient but more complex to have it under separate read and write heads, thereby decreasing head contention and seek times. If the system crashes, the log file will contain 0 or more transactions. Any transaction it contains were not completed to the file system, even though they were committed to the operating system, so they must now be completed. The transactions can be executed from the pointer until the work is complete, so that the file system structures remain consistent. The only problem occurs when a transaction was aborted, that is, was not committed before the system crashed. Any changes from such a transaction that were applied to the file system must be undone, again preserving the consistency of the file system. This recovery is all that is needed after a crash, eliminating any problems with consistency checking. A side benefit of using logging on disk metadata updates is that Those updates proceed much faster than when they are applied directly to the on-disk data structures. The reason is found in the performance advantage of sequential input-output over random input-output. The costly synchronous random metadata writes are turned into much less costly synchronous sequential writes to the log-structured file system's logging area. Those changes, in turn, are replayed asynchronously via random writes to the appropriate structures. The overall result is a significant gain in performance of metadata-oriented operations such as file creation and deletion. Other solutions. Another alternative to consistency checking is employed by Network Appliance's WAFL file system and the Solaris ZFS file system. These systems never override blocks with new data. Rather, a transaction writes all data and metadata changes to new blocks. When the transaction is complete, the metadata structures that pointed to the old versions of these blocks are updated to point to the new blocks. The file system can then remove the old pointers and the old blocks and make them available for reuse. If the old pointers and blocks are kept, a snapshot is created. The snapshot is a view of the file system before the last update took place. This solution should require no consistency checking if the pointer update is done atomically. WAFL does have a consistency checker, however, so some failure scenarios can still cause metadata corruption for details of the WAFL file system. ZFS takes an even more innovative approach to disk consistency. It never overrides blocks, just like WAFL. However, ZFS goes further and provides check summing of all metadata and data blocks. This solution, when combined with RAID, assures that data are always correct. ZFS therefore has no consistency checker. More details on ZFS are found. Backup and restore. Magnetic disks sometimes fail, and care must be taken to ensure that the data lost in such a failure are not lost forever. To this end, system programs can be used to back up data from disk to another storage device such as magnetic tape or other hard disk. Recovery from the loss of an individual file or of an entire disk may then be a matter of restoring the data from backup. To minimize the copying needed, we can use information from each file's directory entry. For instance, if the backup program knows when the last backup of a file was done and the file's last write date in the directory indicates that the file has not changed since that date, then the file does not need to be copied again. A typical backup schedule may then be as follows. Day 1. Copy to a backup medium all files from the disk. This is called a full backup. Day 2. Copy to another medium all files changed since day 1. This is an incremental backup. Day 3. Copy to another medium all files changed since day 2. Day N. Copy to another medium all files changed since day N-1. Then go back to day 1. The new cycle can have its backup written over the previous set or onto a new set of backup media. Using this method, we can restore an entire disk by starting restores with the full backup and continuing through each of the incremental backups. Of course, the larger the value of n, the greater the number of media that must be read for a complete restore. An added advantage of this backup cycle is that we can restore any file accidentally deleted during the cycle by retrieving the deleted file from the backup of the previous day. The length of the cycle is a compromise between the amount of backup medium needed and the number of days covered by a restore. To decrease the number of tapes that must be read to do a restore, an option is to perform a full backup and then each day back up all files that have changed since the full backup. In this way, a restore can be done via the most recent incremental backup and the full backup with no other incremental backups needed. The trade-off is that More files will be modified each day, so each successive incremental backup involves more files and more backup media. A user may notice that a particular file is missing or corrupted long after the damage was done. For this reason, we usually plan to take a full backup from time to time that will be saved forever. It is a good idea to store these permanent backups far away from the regular backups to protect against hazards such as fire that destroys the computer and all the backups too. And if the backup cycle reuses media, we must take care not to reuse the media too many times. If the media wear out, it might not be possible to restore any data from the backups. Segmentation with paging, Multics. The Multics system solved problems of external fragmentation and lengthy search times by paging the segments. Solution differs from pure segmentation in that the segment table entry contains not the base address of the segment but rather the base address of a page table for this segment. Multics address translation scheme as shown in figure. Segmentation with paging, Intel 386. As shown in the following diagram, the Intel 386 uses segmentation with paging for memory management with a two-level paging scheme, Intel 30386 address translation. Segmentation. As we've already seen, the user's view of memory is not the same as the actual physical memory. This is equally true of the programmer's view of memory. Indeed, dealing with memory in terms of its physical properties is inconvenient to both the operating system and the programmer. What if the hardware could provide a memory mechanism that mapped the programmer's view to the actual physical memory? The system would have more freedom to manage memory while the programmer would have a more natural programming environment. Segmentation provides such a mechanism. Basic method. Do programmers think of memory as a linear array of bytes, some containing instructions and others containing data? Most programmers would say no. Rather, they prefer to view memory as a collection of variable-sized segments with no necessary ordering among the segments. Figure below shows programmers' view of a program. When writing a programmer thinks of it as a main program with a set of methods, procedures, or functions. It may also include various data structures, objects, arrays, stacks, variables, and so on. Each of these modules or data elements is referred to by name. The programmer talks about the stack, the math library, and the main program without caring what addresses in memory these elements occupy. She is not concerned with whether the stack is stored before or after the sqrt function. Segments vary in length, and the length of each is intrinsically defined by its purpose in the program. Elements within a segment are identified by their offset from the beginning of the segment, the first statement of the program, the seventh stack frame entry in the stack, the fifth instruction of the sqrt function, and so on. Segmentation is a memory management scheme that supports this programmer view of memory. A logical address space is a collection of segments. Each segment has a name and a length. The address specifies both the segment name and the offset within the segment. The programmer therefore specifies each address by two quantities, a segment name and an offset. For simplicity of implementation, segments are numbered and are referred to by a segment number rather than by a segment name. Thus, a logical address consists of a two-tuple as follows. Normally, when a program is compiled, the compiler automatically constructs segments reflecting the input program. A C compiler might create separate segments for the following: the code, global variables, the heap from which memory is allocated, the stacks used by each thread, the standard C library. Libraries that are linked in during compile time might be assigned separate segments. The loader would take all these segments and assign them segment numbers. Segmentation hardware. Although the programmer can now refer to objects in the program by two-dimensional address, the actual physical memory is still, of course, a one-dimensional sequence of bytes. Thus, we must define an implementation to map two-dimensional user-defined addresses into one-dimensional physical addresses. This mapping is effected by a segment table. Each entry in the segment table has a segment base and a segment limit. The segment base contains the starting physical address where the segment resides in memory, and the segment limit specifies the length of the segment. The use of a segment table is illustrated in figure below. A logical address consists of two parts, a segment number S and an offset into that segment D. The segment number is used as an index to the segment table. The offset D of the logical address must be between 0 and the segment limit. If it is not, we trap to the operating system logical addressing attempt beyond end of segment. When an offset is legal, it is added to the segment base to produce the address in physical memory of the desired byte. The segment table is thus essentially an array of base limit register pairs. As an example, consider the situation shown in figure below. We have 5 segments numbered from 0 through 4. The segments are stored in physical memory as shown. The segment table has a separate entry for each segment giving the beginning address of the segment in physical memory or base and the length of that segment or limit. For example, segment 2 is 400 bytes long and begins at location 4300. Thus, a reference to byte 53 of segment 2 is mapped onto location 4300 plus 53 equals 4353. A reference to segment 3, byte 852, is mapped to 3200, the base of segment 3, plus 852 equals 4052. A reference to byte 1222 of segment 0 would result in a trap to the operating system as this segment is only 1000 bytes long. Pros of segmentation. Segment sharing. Easier to relocate segment than entire program. Avoids allocating unused memory. Flexible protection. Efficient translation. Segment table small fit in MMU. Cons of segmentation. Segments have variable lengths. How to fit? Segments can be large. Fragmentation. Shadow volumes. Shadow volume is a technique used in 3D computer graphics to add shadows to a rendered scene. They were first proposed by Frank Crowe in 1977 as the geometry describing the 3D shape of the region occluded from a light source. A shadow volume divides the virtual world in two, areas that are in shadow and areas that are not. The stencil buffer implementation of shadow volumes is generally considered among the most practical general-purpose real-time shadowing techniques for use on modern 3D graphics hardware. It has been popularized by the video game Doom 3, and a particular variation of the technique used in this game has become known as Carmack's reverse. See depth fail below. Shadow volumes have become a popular tool for real-time shadowing alongside the more venerable shadow mapping. The main advantage of shadow volumes is that they are accurate to the pixel, though many implementations have a minor self-shadowing problem along the silhouette edge, see construction below, whereas the accuracy of a shadow map depends on the texture memory allotted to it as well as the angle at which the shadows are cast. At some angles, the accuracy of a shadow map unavoidably suffers. However, the shadow volume technique requires the creation of shadow geometry which can be CPU intensive depending on the implementation. The advantage of shadow mapping is that it is often faster because shadow volume polygons are often very large in terms of screen space and require a lot of fill time, especially for convex objects, whereas shadow maps do not have this limitation. Simple volumes. A simple volume is a portion of a physical disk that functions as though it were a physically separate unit. Simple volumes are the dynamic storage equivalent of primary partitions in Windows NT 4.0 or earlier. When you have only one dynamic disk, they are the only kind of volume that you can create. You can create simple volumes only on dynamic disk. Simple volumes and the data they contain cannot be accessed by or created on computers running MS-DOS, Windows 95, Windows 98, Windows Millennium Edition, Windows NT 4.0 or Windows XP Home Edition that are configured to dual boot with Windows XP Professional or Windows Server 2003 operating system. If you want computers running these operating systems to be able to access the data, store the data on basic volumes. You can increase the size of an existing simple volume by extending the volume onto unallocated space on the same disk or a different disk. To extend a simple volume, the volume must be unformatted or formatted with the version of NTFS used in Windows 2000 or Windows Server 2003 operating systems. With Windows Server 2003, simple volumes can be extended unless they are system partitions, boot partitions, or simple volumes that were formerly partitions on basic disk that were converted to dynamic using Windows 2000. By extending the simple volume on the same disk, the volume remains a simple volume and you can still mirror it. You can also extend a simple volume to regions on other dynamic disks on the same computer. When you extend a simple volume to one or more other disks, it becomes a spanned volume. After a spanned volume is extended, no portion of it can be deleted without deleting the entire spanned volume. Spanned volumes cannot be mirrored. For procedures on creating and extending simple volumes, a process must be in memory to be executed. A process, however, can be swapped temporarily out of memory to a backing store and then brought back into memory for continued execution. Figure below shows swapping of two processes using a disk as a backing store. Swapping makes it possible for the total physical address space of all processes to exceed the real physical memory of the system, thus increasing the degree of multiprogramming in a system. Standard swapping. Standard swapping involves moving processes between main memory and a backing store. The backing store is commonly a fast disk. It must be large enough to accommodate copies of all memory images for all users, and it must provide direct access to these memory images. The system maintains a ready queue consisting of all processes whose memory images are on the backing store or in memory and are ready to run. Whenever the CPU scheduler decides to execute a process, it calls the dispatcher. The dispatcher checks to see whether the next process in the queue is in memory. If it is not, and if there is no free memory region, the dispatcher swaps out a process currently in memory and swaps in the desired process. It then reloads registers and transfers control to the selected process. The context switch time in such a swapping system is fairly high. To get an idea of the context switch time, let's assume that the user process is 100 MB in size and the backing store is a standard hard disk with a transfer rate of 50 MB per second. The actual transfer of the 100 MB process to or from main memory takes 100 MB divided by 50 MB per second equals 2 seconds. The swap time is 200 milliseconds. Since we must swap both out and in, the total swap time is about 4000 milliseconds. Here we are ignoring other disk performance aspects. Notice that the major part of the swap time is transfer time. The total transfer time is directly proportional to the amount of memory swapped. If we have a computer system with 4 GB of main memory and a resident operating system taking 1 GB, the maximum size of the user process is 3 GB. However, many user processes may be much smaller than this, say 100 MB. A 100 MB process could be swapped out in 2 seconds compared with the 60 seconds required for swapping 3 GB. Clearly, it would be useful to know exactly how much memory a user process is using, not simply how much it might be using. Then, we would need to swap only what is actually used, reducing swap time. For this method to be effective, the user must keep the system informed of any changes in memory requirements. Thus, a process with dynamic memory requirements will need to issue system calls, request memory function, and release memory function to inform the operating system of its changing memory needs. Swapping is constrained by other factors as well. If we want to swap a process, we must be sure that it is completely idle. Of particular concern is any pending input-output. A process may be waiting for an input-output operation when we want to swap that process to free up memory. However, if the input-output is asynchronously accessing the user memory for input-output buffers, then the process cannot be swapped. Assume that the input-output operation is queued because the device is busy. If we were to swap out process P1 and swap in process P2, then the input-output operation might then attempt to use memory that now belongs to process P2. There are two main solutions to this problem. Never swap a process with pending input-output, or execute input-output operations only onto operating system buffers. Transfers between operating system buffers and process memory then occur only when the process is swapped in. Note that this double buffering itself adds overhead. We now need to copy the data again from kernel memory to user memory before the user process can access it. Standard swapping is not used in modern operating systems. It requires too much swapping time and provides too little execution time to be a reasonable memory management solution. Modified versions of swapping, however, are found on many systems including Unix, Linux, and Windows. In one common variation, swapping is normally disabled but will start if the amount of free memory, unused memory available for the operating system or processors to use, falls below a threshold amount. Swapping is halted when the amount of free memory increases. Another variation involves swapping portions of processes rather than entire processes to decrease swap time. Typically, these modified forms of swapping work in conjunction with virtual memory. Swapping on mobile systems. Although most operating systems for PCs and servers support some modified version of swapping, mobile systems typically do not support swapping in any form. Mobile devices generally use flash memory rather than more spacious hard disks as their persistent storage. The resulting space constraint is one reason why mobile operating system designers avoid swapping. Other reasons include the limited number of writes that flash memory can tolerate before it becomes unreliable and the poor throughput between main memory and flash memory in these devices. Instead of using swapping when free memory falls below a certain threshold, Apple's iOS asks applications to voluntarily relinquish allocated memory. Read-only data, such as code, are removed from the system and later reloaded from flash memory if necessary. Data that have been modified, such as the stack, are never removed. However, any applications that fail to free up sufficient memory may be terminated by the operating system. Android does not support swapping and adopts a strategy similar to that used by iOS. It may terminate a process if insufficient free memory is available. However, Before terminating a process, Android writes its application state to flash memory so that it can be quickly restarted. Because of these restrictions, developers for mobile systems must carefully allocate and release memory to ensure that their applications do not use too much memory or suffer from memory leaks. Note that both iOS and Android support paging, so they do have memory management abilities. Thrashing. If the number of frames allocated to a low-priority process falls below the minimum number required by the computer architecture, we must suspend that process's execution. We should then page out its remaining pages, freeing all its allocated frames. This provision introduces a swap-in, swap-out level of intermediate CPU scheduling. In fact, look at any process that does not have enough frames. If the process does not have the number of frames it needs to support pages in active use, it will quickly page fault. At this point, it must replace some page. However, since all its pages are in active use, it must replace a page that will be needed again right away. Consequently, it quickly faults again and again, replacing pages that it must bring back in immediately. This high paging activity is called thrashing. A process is thrashing if it is spending more time paging than executing. Cause of thrashing. Thrashing results in severe performance problems. Consider the following scenario, which is based on the actual behavior of early paging systems. The operating system monitors CPU utilization. If CPU utilization is too low, we increase the degree of multiprogramming by introducing a new process to the system. A global page replacement algorithm is used. It replaces pages without regard to the process to which they belong. Now suppose that a process enters a new phase in its execution and needs more frames. It starts faulting and taking frames away from other processes. These processes need those pages, however, and so they also fault, taking frames from other processes. These faulting processes must use the paging device to swap pages in and out. As they queue up for the paging device, the ready queue empties. As processes wait for the paging device, CPU utilization decreases. The CPU scheduler sees the decreasing CPU utilization and increases the degree of multiprogramming as a result. The new process tries to get started by taking frames from running processes, causing more page faults and a longer queue for the paging device. As a result, CPU utilization drops even further and the CPU scheduler tries to increase the degree of multiprogramming even more. Thrashing has occurred and system throughput plunges. The page fault rate increases tremendously. As a result, the effective memory access time increases. No work is getting done because the processes are spending all their time paging. This phenomenon is illustrated in figure shows thrashing, in which CPU utilization is plotted against the degree of multiprogramming. As the degree of multiprogramming increases, CPU utilization also increases, although more slowly until a maximum is reached. If the degree of multiprogramming is increased even further, thrashing sets in and CPU utilization drops sharply. At this point, to increase CPU utilization and stop thrashing, we must decrease the degree of multiprogramming. We can limit the effects of thrashing by using a local replacement algorithm or priority replacement algorithm. With local replacement, if one process starts thrashing, it cannot steal frames from another process and cause the latter to thrash as well. However, the problem is not entirely solved. If processes are thrashing, they will be in the queue for the paging device most of the time. The average service time for a page fault will increase because of the longer average queue for the paging device. Thus, the effective access time will increase even for a process that is not thrashing. To prevent thrashing, we must provide a process with as many frames as it needs. But how do we know how many frames it needs? There are several techniques. The working set strategy starts by looking at how many frames a process is actually using. This approach defines the locality model of process execution. The locality model states that as the process executes, it moves from locality to locality. A locality is a set of pages that are actively used together. A program is generally composed of several different localities which may overlap. For example, when a function is called, it defines a new locality. In this locality, memory references are made to the instructions of the function call, its local variables, and a subset of the global variables. When we exit the function, the process leaves this locality since the local variables and instructions of the function are no longer in active use. We may return to this locality later. Thus, we see that localities are defined by the program structure and its data structures. The locality model states that all programs will exhibit this basic memory reference structure. Note that the locality model is the unstated principle behind the caching discussion so far in this book. If accesses to any types of data were random rather than patterned, caching would be useless. Suppose we allocate enough frames to a process to accommodate its current locality. It will fault for the pages in its locality until all these pages are in memory. Then, it will not fault again until it changes localities. If we do not allocate enough frames to accommodate the size of the current locality, the process will thrash since it cannot keep in memory all the pages that it is actively using. Working set model. As mentioned, the working set model is based on the assumption of locality. This model uses a parameter delta to define the working set window. The idea is to examine the most recent delta page references. The set of pages in the most recent delta page references is the working set. Figure working set model below. If a page is in active use, it will be in the working set. If it is no longer being used, it will drop from the working set delta time units after its last reference. Thus, the working set is an approximation of the program's locality. For example, given the sequence of memory references shown, if delta equals 10 memory references, then the working set at time t1 is 1, 2, 5, 6, 7. By time t2, the working set has changed to 3, 4. The accuracy of the working set depends on the selection of delta. If delta is too small, it will not encompass the entire locality. If delta is too large, it may overlap several localities. In the extreme, if delta is infinite, the working set is the set of pages touched during the process execution. The most important property of the working set, then, is its size. If we compute the working set size, WSSi, for each process in the system, we can then consider that D equals to epsilon WSSi, when D is the total demand for frames. Each process is actively using the pages in its working set. Thus, process I needs WSSi frames. If the total demand is greater than the total number of available frames, that is, D is greater than M, crashing will occur because some processes will not have enough frames. Once delta has been selected, use of the working set model is simple. The operating system monitors the working set of each process and allocates to that working set enough frames to provide it with its working set size. If there are enough extra frames, another process can be initiated. If the sum of the working set sizes increases, exceeding the total number of available frames, the operating system selects a process to suspend. The process's pages are written out, swapped, and its frames are reallocated to other processes. The suspended process can be restarted later. This working set strategy prevents thrashing while keeping the degree of multiprogramming as high as possible. Thus, it optimizes CPU utilization. The difficulty with the working set model is keeping track of the working set. The working set window is a moving window. At each memory reference, a new reference appears at one end and the oldest reference drops off the other end. A page is in the working set if it is referenced anywhere in the working set window. We can approximate the working set model with a fixed interval timer interrupt and a reference bit. For example, assume that delta equals 10,000 references and that we can cause a timer interrupt every 5,000 references. When we get a timer interrupt, we copy and clear the reference bit values for each page. Thus, if a page fault occurs, we can examine the current reference bit and two in-memory bits to determine whether a page was used within the last 10,000 to 15,000 references. If it was used, at least one of these bits will be on. If it has not been used, these bits will be off. Pages with at least one bit on will be considered to be in the working set. Note that this arrangement is not entirely accurate because we cannot tell where, within an interval of 5,000, a reference occurred. We can reduce the uncertainty by increasing the number of history bits and the frequency of interrupts, for example, 10 bits and interrupts every 1,000 references. However, the cost to service these more frequent interrupts will be correspondingly higher. Page fault frequency. The working set model is successful and knowledge of the working set can be useful for pre-paging, but it seems a clumsy way to control thrashing. A strategy that uses the page fault frequency PFF takes a more direct approach. The specific problem is how to prevent thrashing. Thrashing has a high page fault rate. Thus, we want to control the page fault rate. When it is too high, we know that the process needs more frames. Conversely, if the page fault rate is too low, then the process may have too many frames. We can establish upper and lower bounds on the desired page fault rate. Figure shows page fault frequency. If the actual page fault rate exceeds the upper limit, we allocate the process another frame. If the page fault rate falls below the lower limit, we remove a frame from the process. Thus, we can directly measure and control the page fault rate to prevent thrashing. As with the working set strategy, we may have to swap out a process. If the page fault rate increases and no free frames are available, we must select some process and swap it out to backing store. The freed frames are then distributed to processes with high page fault rates. Concluding remarks. Practically speaking, thrashing and the resulting swapping have a disagreeable large impact on performance. The current best practice is implementing a computer facility to include enough physical memory whenever possible to avoid thrashing and swapping. From smartphones through mainframes, providing enough memory to keep all working sets in memory concurrently, except under extreme conditions, gives the best user experience. Virtual file systems. The previous section makes it clear that modern operating systems must concurrently support multiple types of file systems. But how does an operating system allow multiple types of file systems to be integrated into a directory structure? And how can users seamlessly move between file system types as they navigate the file system space? We now discuss some of these implementation details. An obvious but suboptimal method of implementing multiple types of file systems is to write directory and file routines for each type. Instead, however, most operating systems, including Unix, use object-oriented techniques to simplify, organize, and modularize the implementation. The use of these methods allows very dissimilar file system types to be implemented within the same structure, including network file systems such as NFS. Users can access files contained within multiple file systems on the local disk or even on file systems available across the network. Data structures and procedures are used to isolate the basic system call functionality from the implementation details. Thus, the file system implementation consists of three major layers as depicted schematically in figure below. Figure shows schematic view of virtual file system. The first layer is the file system interface based on the open function, read function, write function and close function calls and on file descriptors. The second layer is called the Virtual File System VFS layer. The VFS layer serves two important functions. It separates file system generic operations from their implementation of defining a clean VFS interface. Several implementations for the VFS interface may coexist on the same machine, allowing transparent access to different types of file systems mounted locally. It provides a mechanism for uniquely representing a file throughout a network. The VFS is based on a file representation structure called a vNode that contains a numerical designator for a network-wide unique file. Unix inodes are unique within only a single file system. This network-wide uniqueness is required for support of network file systems. The kernel maintains one vNode structure for each active node, file, or directory. Thus, the VFS distinguishes local files from remote ones, and local files are further distinguished according to their file system types. The VFS activates file system-specific operations to handle local requests according to their file system type and calls the NFS protocol procedures for remote requests. File handles are constructed from the relevant vNodes and are passed as arguments to these procedures. The layer implementing the file system type or the remote file system protocol is the third layer of the architecture. Let's briefly examine the VFS architecture in Linux. The four main object types defined by the Linux VFS are the inode object, which represents an individual file, the file object, which represents an open file, the superblock object, which represents an entire file system, the Dentry object, which represents an individual directory entry for each of these four object types. The VFS defines a set of operations that may be implemented. Every object of one of these types contains a pointer to a function table. The function table lists the addresses of the actual functions that implement the defined operations for that particular object. For example, an abbreviated API for some of the operations for the file object includes int open command, open a file, int close command, close an already open file, ssize tread command, read from a file, ssize twrite command, write to a file, int mmap command, memory map a file. An implementation of the file object for a specific file type is required to implement each function specified in the definition of the file object. The complete definition of the file object is specified in the struct file operations, which is located in the file /usr/include/linux/fs.h. Thus, the VFS software layer can perform an operation on one of these objects by calling the appropriate function from the object's function table without having to know in advance exactly what kind of object it is dealing with. The VFS does not know or care whether an inode represents a disk file, a directory file, or a remote file. The appropriate function for that file's read function operation will always be at the same place in its function table, and the VFS software layer will call that function without caring how the data are actually read. Virtual memory. We discussed various memory management strategies used in computer systems. All these strategies have the same goal: to keep many processes in memory simultaneously to allow multiprogramming. However, they tend to require that an entire process be in memory before it can execute. Virtual memory is a technique that allows the execution of processes that are not completely in memory. One major advantage of this scheme is that programs can be larger than physical memory. Further, virtual memory abstracts main memory into an extremely large, uniform array of storage separating logical memory as viewed by the user from physical memory. This technique frees programmers from the concerns of memory storage limitations. Virtual memory also allows processors to share files easily and to implement shared memory. In addition, it provides an efficient mechanism for process creation. Virtual memory is not easy to implement, however, and may substantially decrease performance if it is used carelessly. In this chapter, we discuss virtual memory in the form of demand paging and examine its complexity and cost. Background. The memory management algorithms outlined in previous chapter are necessary because of one basic requirement: the instructions being executed must be in physical memory. The first approach to meeting this requirement is to place the entire logical address space in physical memory. Dynamic loading can help to ease this restriction, but it generally requires special precautions and extra work by the programmer. The requirement that instructions must be in physical memory to be executed seems both necessary and reasonable, but it is also unfortunate since it limits the size of a program to the size of physical memory. In fact, an examination of real programs shows us that, in many cases, the entire program is not needed. For instance, consider the following. Programs often have code to handle unusual error conditions. Since these errors seldom, if ever, occur in practice, this code is almost never executed. Arrays, lists, and tables are often allocated more memory than they actually need. An array may be declared 100 by 100 elements even though it is seldom larger than 10 by 10 elements. An assembler symbol table may have room for 3000 symbols, although the average program has less than 200 symbols. Certain options and features of a program may be used rarely. For instance, the routines on US government computers that balance the budget have not been used in many years. Even in those cases where the entire program is needed, it may not all be needed at the same time. The ability to execute a program that is only partially in memory would confer many benefits. A program would no longer be constrained by the amount of physical memory that is available. Users would be able to write programs for an extremely large virtual address space, simplifying the programming task. Because each user program could take less physical memory, more programs could be run at the same time with a corresponding increase in CPU utilization and throughput, but with no increase in response time or turnaround time. Less input-output would be needed to load or swap user programs into memory, so each user program would run faster. Thus, running a program that is not entirely in memory would benefit both the system and the user. Virtual memory involves the separation of logical memory as perceived by users from physical memory. The separation allows an extremely large virtual memory to be provided for programmers when only a smaller physical memory is available. Figure below. Virtual memory makes the task of programming much easier because the programmer no longer needs to worry about the amount of physical memory available. She can concentrate instead on the problem to be programmed. The virtual address space of a process refers to the logical or virtual view of how a process is stored in memory. Typically, this view is that a process begins at a certain logical address, say address 0, and exits in contiguous memory as shown of virtual address space. Recall that in fact physical memory may be organized in page frames and that the physical page frames assigned to a process may not be contiguous. It is up to the Memory Management Unit, MMU, to map logical pages to physical page frames in memory. Note in figure below virtual address space that we allow the heap to grow upward in memory as it is used for dynamic memory allocation. Similarly, we allow for the stack to grow downward in memory through successive function calls. Virtual address space, as shown in figure. The large blank space or hole between the heap and the stack is part of the virtual address space but will require actual physical pages only if the heap or stack grows. Virtual address spaces that include holes are known as sparse address spaces. Using a sparse address space is beneficial because the holes can be filled as the stack or heap segments grow, or if we wish to dynamically link libraries or possibly other shared objects during program execution. In addition to separating logical memory from physical memory, virtual memory allows files and memory to be shared by two or more processes through page sharing. This leads to the following benefits. System libraries can be shared by several processes through mapping of the shared object into a virtual address space. Although each process considers the libraries to be part of its virtual address space, the actual pages where the libraries reside in physical memory are shared by all the processes, figure below. Typically, a library is mapped read-only into the space of each process that is linked with it. Similarly, processes can share memory. Recall from previous chapter that two or more processes can communicate through the use of shared memory. Virtual memory allows one process to create a region of memory that it can share with another process. Processes sharing this region consider it part of their virtual address space, yet the actual physical pages of memory are shared, much as is illustrated. Pages can be shared during process creation with the fork function system call, thus speeding up process creation. We further explore these and other benefits of virtual memory later in this chapter. First, though, we discuss implementing virtual memory through demand paging. Virtual disk. Virtual disk and virtual drive are software components that emulate an actual disk storage device. Virtual disks and virtual drives are common components of virtual machines in hardware virtualization, but they are also widely used for various purposes unrelated to virtualization, such as for the creation of logical disks. Operation. A virtual drive is a software component that emulates an actual disk drive, such as an optical disk drive, a floppy disk drive, or a hard disk drive. To other programs, a virtual drive looks and behaves like an actual physical device. A virtual disk may be in any of the following forms. Disk image, a computer file that contains the exact data structure of an actual storage device. Logical disk, also known as VDisk, an array of two or more actual drives that cooperatively act like a single device. RAM disk, which stores its data in random access memory, RAM, instead of a storage device. Uses. In hardware virtualization, virtual machines implement virtual drives as part of their efforts to emulate the behavior of an actual machine. As with an ordinary computer, a virtual machine needs one virtual drive and one disk image to start up, except when it is performing a network boot. More virtual drives are added as needed. Virtual optical drives are used in physical computers to transfer the contents of the optical disks onto hard disk drives. Doing so helps in resolving the problem of the short lifespan of CDs and DVDs and takes advantage of the faster data transfer rate of hard disk drives. However, virtual optical drives are also used for software piracy. Early computer games used disk existence verification to ensure licensed use, which can be circumvented using virtual optical drives. As a countermeasure, the Star Force copy protection scheme attempts to thwart disk virtualization. Modern video games have migrated to online product activation as part of their distribution process. Conclusion. In this chapter, we have covered the following in detail. Memory management, logical versus physical address space, swapping, contiguous allocation, paging, segmentation, segmentation with paging. Virtual memory, demand paging, performance of demand paging, page replacement algorithms, thrashing, demand segmentation, file. system interface, access methods, directory structure, protection, consistency semantics, partitions, simple volumes, shadow volumes, virtual disks, BitLocker. File system implementation, file system structure, allocation methods, free space management, directory. Implementation, efficiency and performance, recovery.